My name is Sara Nurollahian. I'm interested in a student's use of pattern and anti-pattern, so I start showing you an example of anti-pattern in a student code. Here, a student repeated the same line of code in if branch and else branch. We want them to factor out the repeated code so the code will follow the expert pattern. Because while programming patterns and anti-patterns can exhibit the same behavior, anti-patterns make the code harder for others to read, understand, and modify. However, anti-patterns occur frequently in a student code. We know this from a wealth of work on analyzing a student's homework and other writing tasks. It makes sense to conclude that students who use anti-patterns aren't sure of how to use correct pattern. Here we ask, does code writing alone show a complete picture of a student knowledge? From prior work, we know that code writing can sometimes overestimate a student's knowledge, as a student can generate code without understanding the underlying principles. But it can also underestimate a student's knowledge. Students might know how to correctly use patterns, but they might not be motivated to do so, especially if they are only being graded for code functionality. We address our main research question with two subparts. First, to what extent do anti-patterns on a writing task indicate knowledge gaps? We explored this by giving a student a chance to revise their own code and seeing what levels of hint they need to do so. Next, when a student uses a pattern or anti-pattern in their code writing, how useful is that for predicting their success in editing that type of anti-pattern out of someone else's code? We surveyed 328 CSS students across 2 courses. The survey was online, it was self-paced, and a student had 1 week to complete the survey to receive the extra credit. I discussed the task and results by research question, not in the order that a student saw them in the survey. Code writing task. Code writing tasks describe the expected behavior of a simple method, like when the input starts with A, return true, otherwise return false. Students were given the method signature and asked to fill in the method body. All writing tasks could be done with less than 10 lines of code. Students who wrote with anti-pattern in the code writing section were prompted to revise and were given progressive hints if needed. For example, student code was prompted for the revision after they returned Boolean literals with if and else rather than returning the expression directly. For code editing, all students were asked to edit the functional code that used an anti-pattern. They were not told what was the anti-pattern or how to fix it. All of the tasks targeted 3 pedagogically important programming patterns. The first 2 patterns were very similar. They were returning Boolean expression with 1 operators and 2 method calls. A student code for this programming pattern was flagged for revision if it included any if statements. The third pattern was unique versus repeated code within an if and else that we already discussed. Given our task, code was flagged for revision if it had an else or had more than 1 return statement. With data from this task, we first wanted to know if writing with an anti-pattern indicates a knowledge gap. So we examined how much support do students need to revise their own code. This is a student response to code writing prompt for returning Boolean expression with method call. Since they used if statements, their code got flagged for the revision and they saw the first prompt. The prompt asks the student to copy and paste your code into the box below and see if you can improve its style. This prompt does not say what's wrong with the code or how to fix it. This prompt should help students who know how to correctly use pattern but are not motivated to using that. However, it should not help a student with deep conceptual gaps. The student revised the code after the prompt by making the explicit else implicit. Therefore, their code got flagged again and they saw the hints. The hint suggested question a specific control flow to use or avoid. and ask a student if they could follow the suggestion. Here, the hint asks, can you rewrite the code without an if statement? A student could answer yes, and if they answered yes, they were given their final chance of revision. And if they answered no, which is the case with this student, they were given two worked examples. One example showed the code with the targeted on-type pattern, and the other one followed the expert pattern. The prompt asks students to check out these examples. They do the same thing and see if you can follow the prompt. Finally, students directly returned the Boolean expression with method call. Now let's see how students performed starting from code writing and students who wrote expert pattern, percentage of a student who succeeded after first prompt, a student who succeeded after seeing the hints, a student who succeeded after worked example, and a student who did not succeed after all revision opportunities. The gray background shows that the survey mistakenly not flagged some of the code that it should. We can see that a student's knowledge varied based on pattern. Returning Boolean expression were easier overall, and more students correctly wrote with expert pattern in their initial try. Now let's zoom into only students who use on-type patterns in their writing and see how they performed in revision. For returning Boolean topics, which are the first two topics, more than 55% of the students who wrote with on-type pattern could revise their own code at the first prompt and without receiving extra information. Therefore, these students' usage of on-type pattern in code writing is not due to conceptual gap. However, for unique versus repeated code, a student showed less understanding, and only 6% of the students who wrote with on-type pattern could revise the code without extra information. Therefore, these results can answer our research question. On-type patterns for returning Boolean topic were not due to large conceptual gap, but on-type pattern for repeated code was. Now let's see RQ2 that asks how useful is code writing as a predictor of a student's success in editing someone else's code. Note that only a student whose code was flagged for on-type pattern did the code revision, but all of the students did the code editing. Here's an example of code editing task for returning Boolean expression with method call. Each editing task targeted some on-type patterns and asked the students to improve the style without changing the functionality. The students were not told what to improve or how to improve. Here's the successful editing that directly returns the Boolean expression. We examined the relationship between writing style and editing success for each topic. These are students who wrote and edited successfully. These are students who wrote and edited unsuccessfully. And the middle shows the students who succeeded in one task, but not in the other one. Overall, the performance of most students is aligned, meaning that most students were successful in both writing and editing tasks, or neither. Chi-square tests for each topic show that this correlation between the two tasks is significant. However, logistic regression shows that code writing only accounted for 15% of the variance in editing or less. Now we can answer RQ2. Since code writing is correlated with editing success, but only weakly predicts it, these results show the value of measuring a student knowledge with editing tasks in addition to the code writing. In sum, we found that code writing alone does not show an accurate view of a student knowledge. Therefore, when we design our own task, we should also include other tasks besides code writing to better understand a student's knowledge. We already talked about some other ways of measuring a student knowledge. Here is some more. We can also give a student some comprehension questions. We can ask them to identify the expert pattern. We can ask them to select the code that is most readable to them. And actually, we have these two tasks in our study, but here we didn't talk about. So feel free to check out the paper, as you can see how these tasks can be useful predictors of student knowledge and other tasks. even if we don't have, even if we only have access to students' programming submissions, looking at both instances of anti-pattern and pattern together will provide us with a better picture of student knowledge. Here's a summary of my talk. As you can take a look, I will be happy to answer any question.
Thank you so much. So, do we have questions? Yes?
Sorry, going to do the thing. Not so much a question, but an endorsement. I so am happy to see more people focusing not just on intro CS is writing. Like, I think we have to be moving to reading, especially in the post-ML world. So like, I just want to applaud that direction and the research that you're doing there. So thanks.
Yes, absolutely.
Thank you. So one quick question. So if we start, one thing that I was thinking while watching your presentation, what would be your main recommendation if we start a course like based on your findings? What would you recommend for it, like a teacher if we use some of your findings?
Yes, we definitely encourage instructors to use other tasks rather than code writing. For example, many students may know how to correctly use patterns, but they may not know where's the best places to use, or may have difficulties identifying where they should use pattern. Therefore, code revision and code editing tasks, which are technically the refactoring tasks of other people or their own code, would definitely help the students.
Good. All right. Any other question? No? So thank you very much again for joining us, presenting.
Thank you.
Okay, thank you very much. I'm Natalia Silvis, and I present an assignment that we did for software testing. Fritz Hager is a retired medical physicist, and I will explain you in a minute why we had this cooperation, which seems strange, I think, for computer science. The problem, I will show you our assignment, some lessons learned, and conclusions and future work. The problem we want to solve is well known for software testers, educators. We want our students to design tests, to execute them over and over again, until they find bugs or they don't find bugs. In the end, we say, now you're ready and you have to get a grade. This is very boring. So even if testing is very crucial for a safe society, students don't like to test. They prefer to code, they prefer to design, they prefer to make money. They don't like to test. So the question we answer here is how to motivate software testing beginners. So we designed an assignment. So you see we have lectures, 7 weeks of all kind of theory for testing that everybody knows. But what we did is maybe more original in a way, is to design an assignment in the beginning called Failed, where we scare our students with the consequences of suboptimal testing. So it's an introductory course. I had every year 50, now I have 100 master students, and it's a software engineering track. So we collected 13 accidents that happened in the past. I mean, luckily we are living now in a more safe society, but we still can learn from accidents that happened in 80s, in 90s, but as you see also in 2000 as well. So I'm kind of, yeah. I asked them if they know something about the accidents, and as you can see, the blue lines show that the accidents were rather unknown for our students. So they were really a surprise that software could create accidents in the past. So the assignment was like this. We had groups, and each group had to analyze THIRAC 25 accident, compulsory, because we can learn a lot. I will show you in a minute. And then analyze another accident from this list, and then present in the class their assignment so that everybody hears in the end about 13 possible accidents. And you see the losses are different. There are financial losses, but also brand image losses, but also lives. And this is where we can impress our students. The methodology is an extension of STAMP. STAMP is a method designed by Nancy Leveson at MIT that is using systems thinking to explain accidents. So in this theory, accidents are not happening because a component is behaving wrongly, but because we lose control. So the control between components is in degraded condition, flawed. So then we ask the students, which controller didn't prevent the accident? Then we ask, very important question, why this controller didn't prevent the accident? Then we ask which testing could have prevented, and then what we can learn. So if we have a small example, the recent accidents with Boeing 737 MAX, where a software module called MCAS pushed the nose of the plane down in the moment when it shouldn't do this. Why? Because it was receiving a wrong information about the angle of attack, these sensors here. And you see we have these controllers, we have the software, and we can say, here you can also see how the MCAS was pushing the nose down and the pilot was trying to restore the plane. And then the MCAS was pushing again the nose down until the plane crashed. Then you can say, okay, the problem was the software, of course, but we can also see that the problem was with a manufacturer which could have tested the software. The problem was with a pilot who couldn't disconnect it. The problem was with an airline which didn't train the pilots. So you see, when you analyze the accident, you get a lot of controllers that could have done something but didn't do it. When we know this, then we move to the question, indeed, why? And sometimes the question why can be answered very easily, like a sensor was broken, and what can you do about it and how to test it? Well, just put two sensors, write some software, compare the values between the sensors, and make an error when the things are not equal. But what about here? Why didn't Boeing test their software? Why the company didn't train the testers, the pilots? We don't know. So the students have to learn that investigation of accidents have some questions that will be never answered. What we can do is to ask people who were present there. So this is something that I added in this assignment. And we analyzed 2 accidents of overdoses in a radiotherapy. Radiotherapy, to explain you very fast, is a method to treat cancer. And you treat it with ionizing radiation of very high energy. You see, you have an accelerator and you shoot a beam on the tumor. Everything in TEVAC 25 was controlled by a computer. And you guess already, you are software engineers, you could select 2 modes, electrons and X-rays, in software. And what happened is that what was here was not here. So the hardware was not following the software. And as a result, at least 2 people in this center were killed. And this is something that is also important for us as software engineers. This is not only a problem of the manufacturer. So you see the software was wrong, but also other people. And I found a medical physicist who was working at that time. And we interviewed him with the class, just to show you a little bit of the... Do we have sound?
Room within about 15 seconds. I was sitting at my desk. They said, we got another malfunction 54. I got up and went into the room. The patient was just getting off the table. And I could tell just from looking at the patient that something really serious had happened to this guy. He was hurt bad. I think that realization drove me to try to figure out what happened, because I knew he was badly hurt. The first patient, I was not in the clinic when he was treated, and so people were telling me what happened, and there just wasn't that personal connection with how bad it really was.
Right. Thank you very much.
So when I asked the students what they think about the assignment, as you see, I think the majority agreed that they could see the consequences of suboptimal software testing, and they consider that this assignment is a good beginning for a software testing course. Of course, I think the most important thing they discovered is that by making software, in fact, put a little weapon in the hands of innocent people. And this is something that they should remember, that it's not important only to make a software that is functionally correct. The software should be safe, because if it misbehaves, other people will suffer all their lives. First, that they will die. The second, the ones who are sitting there behind the computer also have a kind of guilt until their death, in fact. And then what we discovered is that a software engineer should also know more about the domain they are programming for. So you don't only sit behind the computer and write code. You should think about what is the system, what are the risks, what is the energy I'm using, can I kill somebody with my software? So you see a lot of emotions. They were sad, they were angry, they were eager, they got courage to overcome their fears. So I think it's very important to engage them emotionally.
Very good questions overall.
Yes.
Because it was a very emotional event on the second event, and you do feel a big burden of responsibility, and even informing people, and you feel like their response wasn't adequate, that you don't stop there. You have to be satisfied that you've taken it to the point where you've got people that know more than me involved, to where you know exactly what the problem is. And say Nancy Levinson, we hired her as a consultant, as an expert consultant, and she was able to look at the software and see the problems. So that was a big help. But just to not stop until you fully understand what happened.
And this way you have peace as well, I think.
Yeah.
So in this way, I think he has peace and maybe feels less guilty for what happened with the system that other people built. So my lesson learned are that I think fail motivates the students to thoroughly test. Meeting with a witness is not necessary, but it enhances the learning effect. On the other hand, we have a pool of examples that we can use when we teach testing, because now we can say, we will teach you today integration testing because we want to prevent accidents like the lost lose of Mars orbiter. Or we want to teach you input validation to prevent other accidents. So we have good examples to introduce our testing techniques. Also, we teach students learn how to extract safety-related requirements and safety-related test scenarios, because except from extracting tests from your functional requirements, you add more test cases. Like, okay, for the Boeing example, just simulate that the sensor is broken and see if the software will generate an alarm and an error message. So students learn how to test for safety, which is something else than test for functionality. Oh, I think I had one more. So in conclusion, we presented a rather unusual assignment where software engineers learn from accidents. It is a multidisciplinary approach. I mean, you need information from safety science, you need information about hardware, about physics, about psychology, because Why do people behave the way they do, and why they deny that they made mistakes? And it's very interesting to experiment with these accidents. We want to create a repository of artifacts with these videos, with these narratives. We want to make a physical replica of Therac 25 just to be open for other teachers and students, because these people, these witnesses will disappear one day, and I would like everybody to know what happened and to learn. We want to add new accidents. Luckily, we don't have a lot of software-related accidents nowadays, but we can go to incidents, near misses. This happens every day in medical world, for example. I'm sure that in every industry we have almost accidents where we can learn from. And I would like to encourage witnesses of accidents to break the silence and share their experiences with software engineering students. It is very emotional and it is very painful to talk about mistakes, but the learning effect is huge. We will educate better software engineers in this way. So I would like to thank my university, Hans van Vliet, who gave me this idea a long time ago, Nancy Liverson for teaching me STAMP, all non-software engineers concerned about safety, because we are here together. We are not only software engineers, we also need the users to work together. My department, my students that always support me, and a Comenius Teaching Fellow grant that made possible this project. This is a replica of Therac 25 that we are building in our university. Thank you very much. I'm open for questions.
Hello, I'm Parvez from Dalhousie University, Canada. I just wanted, can you please go back to the slide in the response of bar chart, how the student felt? No, there was a bar chart showing how the student felt about testing.
Oh, the bar chart. This one? No.
Yeah.
No, this one.
Yeah. This one, yeah. So I see actually one strong disagree there. Can you? Did you get back to the students why he or she feels that way?
I think maybe they didn't understand the question, and they wanted to say very positive and they answered very negatively. I think it's a mistake. I cannot believe, or somebody who was very angry on me. I don't know, but I don't think I have enemies in the class. But it's very weird. But this year I had the same question, and I know a student who said, "Oh, sorry, can you open again the survey, because I wanted to say that everything is positive, but I pressed the wrong button." It happens also in surveys. I hope so, because otherwise, I think after you read 13 examples, you cannot believe. You are right.
Just the wording of the question. It says, it helped me realize. If they came into it already knowing that, they may believe that it didn't help
they didn't
them realize.
Yeah, you're right. Maybe they didn't learn anything new. Yeah. Maybe, I think you are right.
Thank you again.
Okay, so good afternoon from my part as well. So I'm Tomi, coming from University of Helsinki, and I'm presenting our paper about what can be called a software startup within a university. Or this is more about the experiences, how it might help producing industry-ready graduates. So this is joint work with Sara, Petri, Jami, and Matti, based initially on the master's thesis of Saara. So what we actually call this startup like a software development academy, or actually we call it TOSKA, but that's from Finnish. That's for English and Software Development Academy, or SDA for short. It was established a few years ago to develop in-house tools for the university. Okay, of course we had earlier also development of tools by faculty members and so forth, but the problem with those was typically that they are this kind of one-person shows, which creates some troubles, for example, managing them, that if they somehow leave out from the university, then nobody will touch the code and so forth. So we wanted, in addition to making this affordable, the development, we also wanted to make it that it would be professionally not only made, developed, but also maintained. And there are currently active portfolio of 6 systems, which are typically study-related systems. Most of them are used university-wide, and the largest has something like 1,000 daily users at the peak times. And then there is this important element of having paying customer within the university. Okay, it's internal money and it's not that much, but nevertheless, there is this element of someone paying for it. And just to give you some idea, these are the 6 systems, and they are kind of, I'm not going to go into details, but there are kind of some, for example, this one is course feedback system, that is the one that gets those 1,000 users a day at sometimes. It's used by all courses. And then there are systems like a study program dashboard, which is used by all bachelor and master's study programs. And then, for example, this system is something that visualizes the data. I mean, all these lines are for single students and their accumulation of credit points. And now these program managers or the directors can actually take a look at study administration at how they are collecting points in different, by filtering for different student years and different kind of ways of looking at it, how things are going, whether there are some courses that cause trouble and whatnot. Anyway, so then there are our principles for this SDAR. First of all, it's based on the circulation of students. So that they get 1-year contracts, and one reason for that is that we don't want anyone to be too attached to a software, so that it would be kind of a responsibility of a certain person for too long. And then there's the other side of this coin, is that students also have the incentive of looking for employment elsewhere. That's the idea. It's not the idea that this would be their kind of a permanent position for long. And because they know it in advance that it's going to be 1-year contract, that also makes it clear for them that, okay, this is just to give them better position in the market. And they work half-time during semesters, full-time during summer, very flexibly, no fixed hours, because they also have some courses to attend, and they can quite flexibly do that during the semester. And then there is one team all the time kind of responsible for each of the systems. And well, they get salary for that. That's one part, because they are employed. And but the recruitment is right straightforward. There's no kind of a fixed time for recruiting new persons, but it's basically when someone leaves, then there's an opening, and then a new student will be recruited to the academia. Okay, so that was to give you the background of what we are talking about when I talked about this SDA. But this study, what we are presenting in the paper, was actually about that how those students experienced it as a learning experience within them. And that's what we try to understand by actually interviewing the alumni, the student who has passed the course and went into the industry for work. And we were able to reach 15 out of the 17 who had passed the course at the time of doing the interviews in March 22. And the key experiences they have, the first one was that it was actually what they gained or experienced that's working with real software that is in production. And I mean, now comparing that to something what they typically do with their capstone projects or student projects, which we also have in this one, it has to work. It has to work continuously, and they have to be kind of take responsibility for that. And that was kind of one real experience what they reported there. And the other one, which was now when they were already working in the industry, what they compared is that in that they got pretty wide responsibility for the system, because they were basically talking to the customers. They were programming everything from the user interface to the backend, so the whole full stack, and even somewhat at least responsible for the running the system. That's what it runs actually all the time, because they were the customers. And compared to their experiences from the industries, that there they typically get the smaller or some kind of more contained tasks to do, whereas in this one they kind of were responsible for many things, and they reported that as a kind of a good experience from having this kind of a wide responsibility. And then of course the employee status and salary, although that's not too much, it was there just to also show that, okay, gave a little bit of a realism into the game as well with that. And one more thing that was, which is actually probably because of Matti Luukkainen, who is running the show, so is that there was a very strong community within the people there, so they were kind of a good ones. And then one part of that is probably also due to the selectivity, because I mean, Matti is handpicking the students for there, and one of the experiences was what these students reported was that as a potentially negative one was this exclusivity of the thing, that okay, it's not for everyone, it was just for those who get picked up there, but okay, that's same with all jobs probably. But I mean, that's something that there is. It's not some students, even if they want, they might not get into that one. But on the other hand, again, if compared to the other student projects they had in this one, everyone had a very high motivation to do things. They were highly motivated, so there were no free riders, there were no just those who are there to get the credit points and so forth. So in this one, that was something that they considered highly kind of a benefit, kind of a good thing about this one. All right, and then something what we thought that how this actually changed, what was got out there and what was being taken into some consideration or actually already acted upon, is one of the downsides. They said that, okay, there was each team has a senior. Well, it's what was one of the students that was senior by a couple of months. So I mean, that's not was not that much seniority in there. Whereas in the industry, there might be someone around who has been working 15 years within the product or area, and of course, there's a totally different level of seniority. We can't get into that, but we are still trying to alleviate the problem a little bit by offering some students an extension, so that there will be actually someone who knows or has a little bit longer experience about program, because these were junior programs, they didn't have any real experience, so now there would be someone having a little bit more. And then also we are trying to hire a full-time developer just to give this kind of someone who has already experience, has background, to give them a little bit more of this kind of a knowledge about software development that they have. It's not to take away from the students a responsibility for the software system, because that's essential part of their experience from this one. So, but it's more to give them someone who can say, okay, that's actually not very wise thing to do, and you might reconsider something like that. So I mean, giving this kind of making these design decisions a little bit more sustainable in the long term. And then something which is something is because they have high freedom and autonomy in organizing the work. There's also the little bit of a problem, a balancing act, so that how to make them to have them as a team working at the same time, whether they are kind of in the office preferably even that, but even if they are remotely working, then they would be kind of working at the same time, have this kind of discussions. And that is something of balancing with the autonomy and flexibility. Okay, then what to take home from here? I have collected here the benefits from the 3 levels. From the university level, we got what was intended for we are getting the tailored software at affordable cost, and it will be professionally maintained. I mean, that's actually, it seems to be working pretty well. And the students are getting the realism, so they are working the real product, not something that they throw away as a prototype once they get their credit points and the project is over. And of course, there's the employment status. But then one thing is that what the Matti is that actually for the teacher, this gives him an incentive to keep up to date with what's going on in software practice and with the tools and so forth. So that everything is here should be kind of up to date all the time. Okay, with that, I thank you for your attention.
Yeah, one question there.
Hi, my name is Sebastian Bock from TU Delft. I'm fascinated by the idea of the STA. So I have 2 questions. One very short clarification questions. A participant, would they also get credit points, or is it like a qualification project after they finish their studies?
No, they do that during their studies, but for this they are being paid, and so they don't get credit points for this one.
Okay, yeah. And then so the actual question is, you call it the development academy. What role does the operation in this case play? Do you provide them with like a readily available Kubernetes cluster, and they are supposed to build the software and deploy it, or is it also that you hire them for operating and providing the infrastructure?
Well, that's a good point. They actually, at the moment, they are running the software on our own servers, and they are, the main responsibility is for the teacher, keeping that running, and then, I mean, he is 24/7 at all ed. But basically, the students do that. I mean, they are capable of doing some of the operations. But this is something that we would like to shift away to the IT department or something that they would take more responsibility for the operations. But they do some of that as well.
Okay, very cool. Thank you.
Yeah, one and the last.
Yeah, thank you for the presentation. And it's a very good idea, but I'm wondering if the system, if your services are quite stable, after that, there is no fascinating request from the customer base. So that means the code is quite stable and a legacy. So what do students coming to the system can run?
So are you asking that the system becomes stable and there's nothing to do? Or?
Yeah, and if the system is quite stable, then how to learn the new things?
Okay, that's a good point. Okay, the systems are being, of course, I mean, there are requests for new features for these systems all the time. And then we have in the pipeline thinking of, again, the new systems. Okay, this is a limited resources, but the idea is that there would be something new to do for them. And at the moment, there has been, I think there are more requests than that can be delivered, actually.
Thank you very much again. Let's take again the speaker.
So, good afternoon to everyone, and thanks for having me here. I am Luigi Quaranta from the University of Bari, Italy, and I'm here to talk about teaching MLOps in higher education through project-based learning, a paper that I wrote with Filippo Lanubila and Silverio Martínez-Fernández. So today, building machine learning models is becoming easier and easier thanks to the large availability of machine learning libraries and frameworks. However, making a production-grade ML-enabled component out of a model prototype is still challenging. To help practitioners solve this challenge, several practices and tools are emerging that we mostly recognized under the umbrella term of MLOps. MLOps is rooted in software engineering and heavily inspired by DevOps, and as such, it places great emphasis on process automation. So given this widespread adoption of data-driven AI, several universities are offering today specialized degree courses and learning paths on machine learning. But so far, the academic focus has been mainly on the construction of high-performance machine learning models, and there has been a general lack of emphasis on MLOps. This is the reason why we decided to design our own university course on MLOps. The prerequisite for this course is that the students need to be already acquainted with ML techniques. They already know how to build machine learning models. And the goal is to teach them how to adopt MLOps practices and provide hands-on experience and provide them with hands-on experience with MLOps tools. As the teaching methodology, we decided to adopt project-based learning, and indeed over the entire duration of the course, the students develop a project assignment in which the goal is the deployment of a production-ready ML component to a cloud service. Last fall, we held this course in 2 different universities, the University of Bari in Italy, as part of the master's degree in computer science, and la Universitat Politécnica de Catalunya in Spain, as part of a bachelor's degree in data science. We organized our course into 6 milestones. During the first milestone, we asked the students to select a problem to solve with ML and describe it using model cards and dataset cards, and to choose how to communicate and coordinate their work. In the second milestone, we focus on the reproducibility of the model training pipeline. We ask the students to be consistent in structuring their project and to version not only their code, but also their data and models using tools like DVC. And also, we ask them to track their experiment using tools like MLflow. Then, in the third milestone, the focus shifts to quality assurance. We teach the student how to analyze the energy efficiency of their training pipelines using Code Carbon. And we stress the importance of statically analyzed both code and computational notebooks using tools like PyLint and PyNVLint. Then we also show how to test the behavior of models with PyTest and the quality of data with Great Expectations. In the fourth milestone, we focus on API development, and the student here need to choose a cloud provider where to use to deploy their application, and then to develop an API to serve the predictions of their models, using, for instance, a framework like FastAPI. In the fifth milestone, we ask students to package their model with its API using a containerization technology like Docker, and to automatize the process for building the Docker image using CI/CD tools like GitHub Actions. In the sixth milestone, finally, the focus is on monitoring. Both resource monitoring, the ML component is seen as a software resource, and so it is monitored using classical tools like Prometheus and Grafana, but also monitoring of the model performance over time to be able to timely detect drifts. We decided to analyze our project-based learning approach to teach MLOps for the purpose of its evaluation with respect to its instructional effectiveness, from the point of view of both instructors and students in the context of university courses. In particular, we focused on 2 learning outcomes: affective outcomes and the quality of artifacts produced by the students. In the fall of 2021, we held a first run of the course, a pilot run before the current edition, and overall we collected positive feedback. All the students were able to deploy their machine learning components to the cloud, and we also learned some lessons. So, for instance, the students found the proposed technologies overall useful and attractive, but some of the tutorials that we gave could be avoided. And instead, we needed to address some additional topic, like model performance monitoring, which indeed was added during this year edition of the course. Thanks for your attention. I'm open to questions.
We have time for question. Yes, one question.
First of all, congratulations for this very interesting experience of teaching MLOps in the university environment. I was just wondering, when I was looking at the steps, are you also, did you teach something related to the requirements of the system, or how much did you emphasize the requirements? I see that you have a very interesting focus on the part of deployment and monitoring. because I also had an experience teaching also in 2021, also software engineering for machine learning. And there we put much emphasis on the requirements, the architecture and design. And I think that you have a very interesting focus on the other parts of like the deployment, monitoring, and that we could maybe exchange some ideas in the direction of coming up with a more complete life cycle coverage on this. But I would like to hear, of course, what was your emphasis on the requirements part and architecture?
Okay, thanks for the question. I go back to the slide where the requirements part is something that we explain in theory during milestone 1, the execution of milestone 1. But we provide the students with this method, which is widespread today thanks to platform like Hugging Face, to describe the characteristics, the requirements, and the characteristics of their models, the model cards. It is a fast way to at least describe the requirements, the basic requirements of the system that they intend to, the component that they intend to develop.
All right. Thank you so much. Yeah, unfortunately, we don't have. We have to start the next one on time. Sorry.
Hello everyone, my name is Abhishek, and I have been exploring this research question, which is how can we learn to write program code and documentation that are enjoyable to read, easy to understand, and easy to maintain. In this talk, I will introduce the concept of software resurrection as a way to address this research question. The software resurrection exercise starts by building and testing a historical software release on a modern hardware and software platform. Any issues encountered during compilation and testing has to be fixed by the learner. The exercise concludes by reflecting on the experiences and then writing a critique about it. Let us see an example of the software resurrection exercise based on the SQLite database engine that was released 20 years ago. As we build the source, we encounter these two issues. So the first issue is caused by compilers dropping support for certain header files. And the second issue is caused by conflict in the identifier names used in the standard library and in the SQLite database engine. Now, both these changes were introduced after the release of the SQLite database engine 20 years ago. After fixing all the build issues, we move on to the testing stage, where we use the test suite that was included in the original software release. We encounter these three issues during testing, where the first two issues are caused by a software dependency library of the test suite, and the third issue is caused by a failing test. After fixing all the test issues, we move on to the next stage where we critically reflect about our experiences. Now, we had these experiences because the hardware and the software platform have changed dramatically in the last 20 years. Let us see an example of how a failing test contributes to learning. So in order to understand the reasons for a failing test, the learner must explore relevant parts of the source code as well as understand the documentation. Good documentation and well commented out code, as shown here, and in this slide, it helps the learner to easily pinpoint the reasons for a failing test. Our investigation shows that this failing test is caused by a test suite that is still living in a 32-bit world, whereas modern computers use 64 bits to store the address of a memory location. From this failing test, we learn that if a test suite is relatively complex, then it will demand a test suite for itself, leading to a recursive dilemma. Therefore, we should prefer a simpler test suite. The software resurrection exercise has helped me grow as a software developer, but you may wonder why this seemingly pointless activity of resurrecting a historical software should have any value as a learning tool. I have found answers to this question in the following two avenues. So first, let us look at how philosophy can help us understand the value of software resurrection as a learning tool. Most of our life experiences and perspectives are constrained by the time in which we live. In an essay written in 1956, Bertrand Russell described wisdom as essentially a process of breaking free from these constraints. The software resurrection exercise enables a learner to view things from different perspectives by introducing them to program code and documentation that are remote in time. The learner, therefore, is no longer captive of their personal viewpoints or the constraints of their time. Thereby, they become capable of surveying a wider horizon of ideas. This, in turn, contributes to growth in their wisdom. Software resurrection exercise can be adapted for large-scale training and education programs by providing a checklist of all the issues that can be encountered in an exercise, or by providing tips and pointers for further exploration, and finally providing a template for writing a critique for students who feel a need for such a template. Let us revisit the research question that was posed at the beginning of this talk. We now understand that engaging with program code and documentation that are remote in time or space helps learner experience the pain and joy of software maintenance. These experiences shows the factors that contribute to readability, intelligibility, and maintainability of a program code and documentation. Let us conclude this talk with this wonderful quote from Harper Lee, which says that you never really understand a person until you consider things from his point of view, until you climb into his skin and walk around in it. I have adapted it to software engineering as follows. You never really understand software engineering until you consider things from software maintainer's point of view, until you climb into the skin of a software maintainer and walk around in it. Thank you very much. I look forward to your questions and advice.
Thank you so much. Can we show him on? Yeah, perfect.
Yes, okay. Hello,
good.
everyone.
So let me ask you one question. We're going to see if the audience has other questions. So can you share with us what are your next steps on this topic and this research?
Yes. So one of the immediate steps that I'm pursuing right now is to do more software resurrection exercises. So currently there is an exercise based on SQLite database, but now I'm pursuing a similar exercise based on the Postgres SQL database. And then in the future, I want to have more such exercises for students to learn. So that is one. The second is to have an online seminar where we present these learnings in a different way so that students can engage with these learnings and then also provide their feedback on whether this type of learning is any useful to them or not, so that I can understand how well or how I can adapt this to different settings and then to a teaching and learning setting.
Good. Do we have any questions from the audience? Yep, 2 questions.
I may have missed this, but I was curious, what level of a course do you do this at? Is this a 3rd or 4th year course or a master's level course, or where do you have them do it?
Yes, so this type of exercise requires some background in compiling a software and then being able to program in a language that like a C language. So my belief is that it can be done in an undergraduate level, but not too early. So maybe later part of undergraduate course where they know how to build programs, they are familiar with the programming language, and then now they are feeling a need to learn more about programming, apart from the syntax and then simple examples. I believe there is no particular stage for learning the art of writing programs that are easy to understand and easy to maintain. So even professionals, they should find it useful, these exercises.
My question is related to my colleague behind me. So what course are you using, and did you consider to use it in a software testing course maybe, because you could say I test my program for readability or for usability. Are you using this assignment in a certain course?
Yes. So I'm not using it in course. I do not have access to students, and I do not have access to classroom settings where I can use these things. So I'm a research software engineer by profession, where I develop software that is based on research. But I'm very keen to see this being tested out in classroom settings. Unfortunately, I don't have the resources to try it, but I'd love to see someone else try it.
Right, maybe there's an opportunity here. Great, so thank you very much for joining us. Let's thank him again.
Thank you very much, everyone. Thank you.
And with that, we conclude this session. Just a reminder that at 5:30 we have the town hall at plenary room number 1, 5:30 to 6:30. Hope to see some or most of you there. Thanks for joining again this session.